Hello, calculus students. I hope you are doing fabulous. We are ready to study section 4.6, gradient. Okay, gradient is one of the most important concepts in calculus 3 in multivariable calculus. And we will finally be able to answer questions like, what is the rate of change as you move from this point in this certain direction that's given? All right, so we have a lot of topics to cover in this one section. Namely, though, the most important thing in this section is the power and the beauty of what we call gradients. Okay, so just focus on what this gradient is, all right? And then with all the wonderful properties of gradient, I hope you like this. All right, let's get started. Okay, so here we will study section 4.6 and we will study gradient and directional derivatives. All right, so assume this, here's a picture of what I want you to see, right? And we are looking at, of course, we are looking at this particular point here, which is x naught, y naught, and the value of the function at that point is z naught, which is the value, f of x naught, y naught, right? But if you look at this from the top, okay, oh yeah, by the way, the question we want to ask is, you see this little blue vector here? That shows you the direction. All right, so the little blue unit vector is showing the direction. And the question is, as you go in that direction, what is the rate of change, okay? And so let's say here is the point, x naught, y naught. You're looking at this from the top. And then this vector seems to be sort of like in the direction of which direction is it? Well, it looks like maybe it's going in this direction, right? And so that's what we will be studying, all right? Let's just make sure we understand what we are talking about. So let's say I'm going to let u be the unit vector. And right, by the way, it doesn't have to be a unit vector, but if it's not a unit vector, as you calculate the directional derivative, you have to make one important correction before you do any calculation. But let's assume first that this is a unit vector, right? And it is showing the direction, or in particular, showing a direction. Okay, and of course, you have infinitely many directions. So we will establish that this angle measured from the positive x-axis, measured from the direction of the positive x-axis, is theta. Okay. Now here, as we know, this is here's a question. Okay, what is the rate of change? Rate of change of what? Of course, f. Okay. In the direction of u. All right, we've already established that, and you can clearly tell if you're standing right here on this surface, it really does depend. The rate of change depends on which direction you go. If you go this way, or this way, or this way, or this way, or this way, right? And so notice here in this picture, the x direction and the y direction, right? And basically what we're going to say is u can be written as a cosine of theta, comma, sine of theta. Now why? Well, because we assume that u is a unit vector, and clearly the cosine of theta is hot. So basically what I'm trying to say is this: if you have this, right? And I know you already know this, but if you have an angle, this is your angle, right? And then this is cosine of theta, and this is the sine of theta, because this length, the hypotenuse, is equal to 1, right? And so that's something that we can just assume just because we know trigonometry. Now, f, the rate of change in the direction of the x-axis is fx, right? So this is the rate of change in the x direction, and fy, we already know the rate of change in the coordinate directions, or the directions of the coordinate axis, right? Now we have to answer this, we are about to answer this question, and as you do this, we will enter into this, or run into or happen to run into a wonderful thing called a gradient, right? So just sort of look forward to it. Just be patient for the maybe next 10 minutes and you will be able to see that. Okay, so here is my notation. So let's try to denote D, capital D, and then followed by F, and we'll put a little U in between them. This is DF in the direction of U. So this is the directional derivative. Okay, and of course, as the derivative, this is the rate of change. Directional derivative of F in the direction of U. Get that? That's precisely what I was talking about. What is the rate of change as you move from x naught, y naught in the direction of U? Okay, so we will be trying to figure out. In fact, I'll write this equation right now. So here's the definition. The way we define this is, of course, you know, how far if you walk in that direction, what is the rate of change? Well, oh yeah, so let's say we calculate this at x naught, y naught, right? So how do you do that? Well, theoretically, right, as far as the mathematics is concerned, the definition is actually pretty easy, right? It's a limit as t approaches 0. I mean, because we know this is the definition of the derivative, okay? It's a long expression here. It's f of x naught plus t cosine theta, right? Because what we're doing is we're actually going, let me see if I can use a different color here. This is the point x naught, y naught, okay? And we're actually going in this direction and with the parameter t, okay, as t approaches 0. So if you go this way for t seconds, let's say, right, then you have moved in the x direction t cosine theta, because the x component is cosine theta, right? And then in the y direction, you start with y naught and then plus t sine theta, okay? And that's just you know, the shift from the position x naught, y naught to in the direction of U with the parameter t. And then of course you subtract the original value f of x naught, y naught, okay? And that is a difference called the delta of f, right? Delta of f or delta z or whatever. And then you divide it by t, okay? So that makes sense because that is how we define the derivative, okay? Now, let's talk about this point here. This is p, x naught, y naught, right? If this point is p after t seconds, okay, this point p is what? Well, it's x naught plus t cosine theta, y naught plus t sine theta. Of course, that's exactly what you're seeing on the top part. But this is your new x coordinate, and this is your new y coordinate, right? In other words, x is x naught plus t cosine theta, and y is y naught plus t sine theta. Okay, did you see what I just did here? What I just did is to write x and t. So now what we have is we have a composition of two functions. We have this f, which depends on x and y, of course, right? And x actually has a parameter t. In fact, x is determined by that number t, right? The parameter. And same for y. Okay, now this looks really familiar, right? Of course it looks familiar because this is our multivariable structure for compositions. So now we get to use, guess what? The chain rule, of course, right? So the chain rule, all right, and which case is that? This is exactly the first case we talked about, right? We have a function of x and y, and x is a function of t, and so is y. They share the same one parameter. And because that's what gives us the a nice way to find this directional derivative, okay? And we are about to find the answer. You know, how do you know, or how do you calculate the rate of change of f in the direction of u? All right, are you ready for this? All right, so df of u is equal to, this is basically df dt, right? Because, I mean, that's exactly what this is defining, right? So maybe I'll color. This whole thing is defining the directional derivative. And if you look at that, it is the derivative of f with respect to t that we are looking for, okay? And that happens to be, and by the way, the theory and notation may be complicated. The actual calculation will be rather easy, okay? And I think you'll like this. But remember this process here, the chain rule tells you that this derivative is the partial of f with respect to x times dx dt. Now, I know what dx dt is because I know x is this, right? And of course, you can tell what that is. Hold on just a minute. And then partial of f with respect to y, and then dy dt. Notice here, because x and y only have one variable each, I'm going to use the English letter d, not the partial notation. Okay, so what is that? Well, that is f sub x, right? This is the partial of f with respect to x. Now, what is the derivative of x with respect to t? Simple, it's cosine of a theta, okay? And this is f sub y times dy dt, but that's again simple, sine of theta. Okay, so it really is a pretty simple thing. This is the formula for the directional derivative. I haven't really finished yet. So the directional derivative, the question of how fast or what is the rate of change of f in the direction of u can be answered by this simple equation. But what? It gets much better than this, okay? If you look at this, this is fx cosine theta plus fy sine theta. Why not pair this way? Fx comma fy dot product cosine theta sine theta. Because we have a name for this second equation, cosine theta sine theta, not the equation vector, right? This is exactly what we call u. That's our directional vector. And so this sounds like a great thing to study, right? Because that two-dimensional vector is very simple. It's just composed of the two partial fractions, right? And I mean, sorry, not the partial fraction, partial derivatives. And so, you know, this is simple. We want to give it a name because this vector turns out to be super, super important. And in case you didn't get the hint yet, this is what we call the gradient, okay? So we're going to name this with this fancy letter, which is the upside down the delta, okay? Some people call it del. Anyway, so this is that, all right? So this is the definition of gradient, okay? And gradient is for z, a function of x and y. The gradient will be a two-dimensional vector, and it is evaluated at every single point on the domain. So here's a definition. Now, the reason we want to give this a special name like this upside down delta f is because right now you are seeing this just as the part of the equation for the directional derivative, okay? And you have to appreciate this nice and elegant formula for the directional derivative that can be written as a very simple and very concise equation. It is just a dot product of the gradient and the unit vector showing the direction. Okay, so this is super important, right? And so it's fitting that it's coming at the very bottom of a page. But it turns out this part becomes a important vector in and of itself, right? So this delta at f, which is fx fy evaluated at x naught y naught, okay, so this is a two-dimensional vector, is called the gradient of f at x naught y naught, right? So now that is defined regardless of u, of course, right? Now u is totally independent. U just gives you any direction you want, and then this gradient, when dotted with the u, will give you the directional derivative. Okay, are we okay so far? So this is sometimes people call it del, and I think that would be a good way to read that if you like. All right, let me give you an example before we go further with this idea. Right? Let's say my function f of x, xy, which is z, is equal to 1/4 x squared plus y squared. All right, now can you picture this, the graph of this equation? Right. What I want you to do is this. I want you to find the gradient, not the gradient, the directional derivative of f in the direction of u at the point 2, 3 in the direction of 3, 4. Okay, now before you go further, if you like to, you can pause this right now and try to work this out. And maybe you want to sketch the graph of this function, or maybe you can tell, oh yeah, that's going to be a paraboloid. I don't know if you can tell that, but you can try to figure this out and then you can come back, right? The calculation itself is pretty easy, but there is one thing I should mention. Maybe you can figure that out too, right? The hint, this is not a unit vector yet, okay? But you can easily make that into a unit vector. All right, so go ahead and do that. All right, so this is a, you can do traces if you like. Let x be equal to 0, and you have y, z is equal to y squared. That's, you know, that would be this parabola here like this. And then if you let y equals to 0, then you have a wider parabola, 1/4 x squared, which is more like, you know, this one here. All right, so you know, it's an elliptical paraboloid, right? The 2, 3 is located somewhere here, right? So if you look at this, this is the point. In fact, f of 2, 3, let's calculate this. That's 1/4 2 square plus 3 square, and that seems to be 1 plus 9, which is 10, right? I don't think if you, I don't know if you need this, okay? But the value of this function is 10. Now you will be going in the direction of 3, 4, right? Where is 3, 4? So you go 3 units here, 4 units here. It's more like this direction, right? So imagine what happens if you're standing, or if you're holding on very tightly because it's a steep slope. If you're standing right here, or if you're holding on, hanging on this paraboloid, maybe outside or inside, you're about to slide down. If you're going in the direction of the blue arrow, then you will probably be moving up, right? You will be going this direction, so you'll be going up. And so the directional derivative should be positive. And in fact, it should be a pretty big number from the picture. Okay, so again, the calculation is easy, right? But before that, this is not a unit vector. And it's very important that you use the unit vector, okay? Because that is how the directional derivative was defined, right? So let normalize it. And to make it u, and that's why I call this v, right, as opposed to u, right? So what is, you know, what's the norm of the vector? Of course, that's the square root of 3 squared plus 4 squared, the most famous Pythagorean triple. That's square root of 25, and that is 5, right? So u, the unit vector we need is 3/5, 4/5. We will use that shortly. All right, you calculate fx, which is very simple. That's you move this 2, right, to the front. So it's 1/2 x. And that's it, by the way. F sub y is 2y. You evaluate this at 2, 3, right? This is my notation again. I do a long line and evaluate at 2, 3. So this will give you a 1, and this will give you a 6. Okay, so what do we just find? Right. So the gradient is 1, 6. Okay, at that particular point. Maybe I should write this little more technical or a little more precise. I should use that notation I just wrote, which is the gradient of f at 2, 3 is equal to 1, 6. All right, and therefore the gradient or the directional derivative in the direction of u is simply the gradient times the, or dotted with the directional unit vector. All right, so this will be 3/5 plus, and what do you get? 24/5, and the answer is 27/5, which is, you know, like what, 5.4, right? And we predicted that this will be a pretty large number because you're going up pretty quickly, and that is the answer. Okay, so I hope you get that. Now, let me just explain why is gradient important, okay? And I will give you a few examples or a few reasons right now. But number one is this. Okay, imagine you have a mountain or a surface with a minimum point, okay, or a saddle point like this. Okay. Now, what happens, do you think, at this point, okay, or at this point, or at this point? Okay. This is, of course, the relative maximum, or you can say local maximum. Yeah, let's use the word local. I think that's the word we use. Okay, so it's local maximum, local minimum, and these are the topics that we will be pursuing later in this chapter. And then this is a saddle point, right? Now notice here, as you go back from here to this way, that's the positive x direction. You know that at the top, fx is going to be 0, right? And if you go from here to here, like in the positive y direction, right at the top, fy is going to be 0. Guess what? The gradient turns out to be 0. Same thing here, of course, it's a minimum, so the gradient is 0. And how about here? If you go in the positive x direction, this is the maximum point. So f of x is 0. And if you go in the y direction, this happens to be the lowest point. Remember, the saddle point is defined as a maximum point in one direction and minimum point in the other. But either way, I mean, in both directions, the derivative, the partial derivative should be 0. So one thing that is super important, and I will just tell you this right now, even though this is a part of a theorem, okay, this is like a trailer, all right? Spoiler, if you will. Basically, it says at any local maximum, minimum, and the saddle point, the gradient is going to be 0, the 0 vector, okay, not the number 0, of course, right? And so finding these extrema end up just being finding the points where the gradient is equal to 0. Very familiar to you because you studied calculus 1, right? And this is pretty much exactly what we do. Okay, but there is something even more important than this, all right? So this is glorious, okay? Let me just highlight this like a sun here. This is super important thing, okay? I cannot emphasize this enough. So here, okay? Too much? Yeah, I know. Okay, so let me explain this, right? So here's the gradient, right? I mean the directional derivative. I said this is the gradient dotted with u. But do you remember what the dot product is? There's another way to write the dot product. And I hope you are quite familiar with that by now, right? The dot product of u and v is the norm of u times the norm of v times the cosine of the angle between them. So this is the norm of u, the norm of the first one, times the norm of u. Remember, u is a unit vector. All right, so where theta is the angle between the gradient and the directional vector. Now remember, the directional vector is, is what we decide. We decide which direction to go. Now this is obviously 1 because it's a unit vector. So it turns out it's just the gradient of, the magnitude of the gradient times the angle between those two vectors. You know what, forgive me, I'm going to change to something else because I used theta in the proof above or in the definition above when we talked about unit vector u. So in order to distinguish this vector, this angle from the other angle, let me just call this angle A, alpha, cosine alpha, alpha. Alpha is the angle between the gradient and u, all right? Now, recall, this is something that you know since you're an infant. The cosine of the angle is always between -1 and +1, right? Okay, so what happens if alpha is 0 and if alpha is 180 degrees? This arrow means if then, okay? So if this is true, then what can you say? What happens if alpha is 90 degrees? I'm using degrees like a child, not like a grown-up man, where we use radians. We can use radians if you like, but right now, just use the degrees. Now, I want you to think about what each of these things imply, all right? And then think for like a 1 minute, and then you come back to the second part of this video, all right? Think really hard and see what these things are telling us.